Let me stress a little something about the mechanism of this reaction, which we will get to study in more detail next semester in the second part of organic. In chapter 21, I believe we will get to study in more detail this. So it involves nucleophilic attack of the oxygen on the sulfur of the thionyl chloride. You have formation of sulfur oxygen with the oxygen bearing 3 lone pairs of electrons. And then you have regeneration of the oxygen sulfur double bond and departure of the chloride, Cl minus. So at this point, we have formed the so-called chlorosulfide intermediate. But notice now that the chlorine comes back and the attack will take place from the backside, right? And so that's why we indicate here that the process is an SN2 process with inversion of the configuration. And so that is very important because the stereochemistry of the primary or secondary alcohol that you are using will determine the stereochemistry of the final product. Similarly, when you perform the reaction with PBr3, phosphorus tribromide, instead of thionyl chloride, again, here you will have formation of a good leaving group, the so-called dibromophosphide intermediate, and then the Br minus, one of the lone pairs of the Br minus, will attack from behind, and again, you should expect that there is inversion of the configuration going through an SN2 process. So let's practice that in this couple of examples. So here we have a reaction of S2 pentanol reacting with thionyl chloride. So what do you expect? Well, here we have a secondary alcohol reacting with thionyl chloride. I would expect that I will have displacement of the OH, and I will have formation of the corresponding alkyl chloride. But what is going to be the stereochemistry? Well, because the OH is a wedge, is pointing to me, so I would expect that the chloride will come from behind, and it will be like that. And what is the stereochemistry of this? It will be Cl followed by the propyl followed by the methyl. It looks like S, but because the hydrogen atom is pointing to me here, so it is the R configuration. So this is the R 2-chloro pentane. And then the next example that I have here. So here we have cyclohexanol. Notice that I didn't put any wedge or dash line on the OH. Why? Well, because there is a plane of symmetry here, right? And because there is a plane of symmetry, actually, there isn't any chirality center. So even though the reaction proceeds with inversion of the configuration, I will not be able to observe that. And so the product that I will obtain will be this, right? It will be the bromide, and there is no necessity to indicate stereochemistry. If I put a wedge or a dash, it's irrelevant. It's not incorrect, but it doesn't mean much. So the next slide that I have here indicates the formation of the tosylate. The reagent that we need to use for preparation of the tosylate is the so-called para-toluene sulfonyl chloride. Para-toluene sulfonyl chloride. In some way, is reminiscent to the reaction with the thionyl chloride, because you have a sulfur-oxygen double bond. Here we have 2 sulfur-oxygen double bonds, but the idea is the same. Lone pair of electrons of the alcohol is attacking the sulfur-oxygen double bond. We have formation of an SO minus momentarily. Then you regenerate the sulfur-oxygen double bond, and you eliminate the chlorine, right? And then the final product that you obtain is the corresponding tosylate. Remember, tosylates are excellent Lewin groups. So we will get to use that for some practical purposes. And because we are having the loss of a proton here, and we are eliminating also a chloride there. So we are producing HCl. That is the reason why we use pyridine in this reaction. Pyridine is right here. Pyridine, it has some basic properties because the nitrogen has one lone pair of electrons. It's a fairly basic compound, so that will be pretty good for trapping the hydrochloric acid that we are producing in this reaction. And so the pyridine, the nitrogen will get protonated, and then the chloride will be the counterion of this pyridinium cation. So that is a very recurrent method for trapping HCl in reactions. You add roughly one equivalent of pyridine, and that will allow you to trap the hydrochloric acid, and that will protect some other functional groups that they may be sensitive to the excess of HCl in the reaction. So here we have a couple of examples that show how nicely we can control the stereochemistry, the overall stereochemistry in a synthetic process. Let's say that you start with R2-octanol. R because we have OH followed by the longer chain, followed by the methyl. It looks like S, but because the hydrogen atom is pointing to us, that's why it is R configuration. If I was performing reaction with PBr3, we know that that reaction proceeds with inversion of the configuration. Yes, inversion of the configuration. And so we have the OH pointing away from us, and then now the bromine is pointing to us, right? And then if I perform a second reaction, this is a nucleophilic substitution reaction in which I'm using ethoxide as a nucleophile. So then now I will go through a second inversion, right? I had an inversion first when I go from the alcohol to the bromide, and then I go through a second inversion when I go from the bromide to the formation of the ether final product. So the bromine was pointing to me, now the ethoxide is pointing away from me. So the overall process, I'm going from the R configuration to the R configuration in the final product because I had two inversions, right? Two inversions is equivalent to a retention of the configuration. So let's contrast that now with this other approach. How about if I prepare the tosylate associated with this alcohol? Well, the reaction is taking place on the OH, so nothing is happening on the carbon atom of the main chain, right? So if I had R configuration to start with, I will still have an R tosylate, right? The tosylate will still retain the same configuration. But then now, in this second step, when I use ethoxide as a nucleophile, so there now I will have inversion of the configuration. So when I look at the overall stereochemistry of the process, I'm starting with the R configuration, and then I have only one inversion, so that's why I'm getting the S configuration in the final product. Notice that in one case, I'm getting a double inversion, or in other words, retention of the configuration, and then in the other case, I get inversion of the configuration. So depending on the product that you want to prepare, at will, you can do it in one way or the other, and you can get the desired stereochemistry. Dehydration of alcohols. Well, we have already learned some methods of dehydration of alcohols, but it was limited only to dehydration of tertiary alcohols. In that case, we were using a mineral acid like HCl or HBr, or even better, even more efficient was the use of sulfuric acid or phosphoric acid. So that was one of the methods of preparation of alkenes that we learned in chapter 7, I believe. But how about secondary or primary alcohols? Well, the primaries, they are very difficult to dehydrate because for primaries, you need to use very, very harsh conditions. But for secondary alcohols, you can use also mineral acids like sulfuric acid or phosphoric acid. Sometimes you need to use some pretty high concentrations, like a 75% sulfuric acid. That is very harsh conditions. So there you will have a protonation of the tertiary alcohol, and then you will have a departure of the water molecule, and then depending on the structure of the tertiary alcohol that you started with, you can have a satisfaction of the Zaitsev's rule, and you can get formation of the most highly substituted alcohol. And so that's why here, out of the two options, the major product will be this, because here you have a tri-substituted alkene. The other alternative product is a di-substituted. That's why it will be the minor product, right? So in the next mini video, we will examine what happens when we have a secondary alcohol. The reaction proceeds with E2 through an E2 elimination process. And because of that, you need to remember that we will have an antiperiplanar requirement. So, and because of that, depending on the particular stereochemistry of the starting material, sometimes we may satisfy the Zaitsev's rule, and some other times we cannot. So in the next mini video, we will examine that in a little more detail.